Okay. Now we prove the second result. The second result, if the Hessian is indefinite, indefinite means that it has a positive and a negative eigenvalue. We choose a positive and negative eigenvalue. Eigenvalues, lambda minus, this is a negative eigenvalue, and positive denoted by lambda plus. Now let H minus be eigenvector of lambda minus. Okay. Then we consider this limit. How to say? So this is our point A. Our point A. This is our R. F is defined in the R neighborhood of A. So H negative. This is the direction of H negative. So we want to restrict our F in this direction, passing A, and in the direction of H negative or H minus. Okay, H minus. So therefore we consider Fa plus Th minus. We want to study this, and H minus is given, therefore T change. And also we can require the H minus to be a unit vector. So for this reason, because for such an Fa plus Th minus, Fa plus Th minus, this is Fa plus the gradient term vanishes because A is a critical point. So this is half of Th minus transport Hessian and Th minus, then plus eta Th minus. Simply insert H equal Th minus. Insert H to be replace the H to be the Th minus in our previous Taylor expansion, the second line in this page. Okay, so we get this equality in blue. For this, therefore we need to study the last term. For the last term, we have limit t goes to 0, eta Th minus T square. But because H minus is a unit vector, so this is nothing but eta Th minus square. Now our eta satisfies the first line, red underline limit is 0. Eta satisfies this condition. Of course, this implies that for the fixed H minus, when t goes to 0, this limit is also 0. This is important. Therefore, our Fa plus Th minus is Fa plus here this part, the t here and the t here, these two t can be take outside the multiplication 2t square. Then the H minus transport gradient of Fa and the H minus, this is nothing but lambda minus h minus norm square. This is the basic property of our. We will call this property at the very beginning in the for the how to say, for the here eigenvector, the inner product of a symmetric matrix which is eigenvector is the eigenvalue multiply the square of the norm of the eigenvector. Okay, so we use this result. We see that here we have this right lower corner of this page. So using this result, the second term in the Taylor expansion becomes half of t square, then h minus norm. H minus is a unit vector, so this result is the final conclusion is that this is lambda minus. So we have nothing. We don't need to write anything. We should add a term. We should add the norm of h minus square here. We should add an h minus here, but this is 1, so we don't add this. We don't need to write this. So this is the second. And finally, we have but we have a lambda minus. Lambda minus could not omit. And we have eta th minus. So to use the result that divided by t squared, the limit is 0, we can rewrite this by fa plus t square half of lambda minus plus eta th minus 2t square. So this is fa plus t square little psi t. H minus is a fixed unit eigenvector of lambda minus. So those between the surrounding by this this is a function of t. This function of t we denote by small psi t, and because this term as t goes to 0, this term goes to 0. So the limit of psi t, you can see that the limit of psi t goes to 0, psi t here is half of lambda minus, which is negative. Okay, so I have no space to write. I will write this in the next page. Remember what we have arrived? We have arrived fa plus th minus is fa equals fa plus t square psi t, where limit t to 0 psi t is half of lambda minus, right? Yes, and this is negative. So by the basic property of limit of function, we see that there exists some epsilon minus positive, such that when t belongs to, or we can write, when the absolute value of t is less than epsilon minus, the psi t is negative. Psi t negative means that fa plus th minus is less than fa. So for our a here, to the direction of H minus this is if the minus is positive when TH minus here, this is TH minus, okay? Because H minus is a unit vector, so the absolute value of T is less than epsilon minus means that TH minus values in this range. For those TH minus here, A plus, sorry. So when A plus TH minus here, the value of F is less than FA. Similarly, consider H plus and lambda plus. We also have epsilon plus positive, such that if T is less than epsilon plus, then FA plus TH plus will greater than FA, because lambda plus is positive. That is to say, we have another direction passing the point A. This is the direction of H positive. So these two inequality, 1 and 2. 1 and 2 tell us that for any small neighborhood of A, the neighborhood contains some point. What kind of point? Those points passing A and in the direction of H minus. I draw one red. For this point, the value of F at those points is less than FA, while the value of F on those points in the direction of H plus is greater than FA. So FA is not local minimizer nor local maximizer. So this proves our theorem. Okay.